Something is wrong with the light. The James Webb Space Telescope was built to see the beginning of everything, to capture the first photons emitted by the first stars in the first few 100 million years after the Big Bang. It is the most precise instrument humanity has ever placed in space. A 21-foot gold-coated mirror floating 1,000,000 miles from Earth at a gravitational stability point, where it drifts in silence, shielded from the sun by a heat shield the size of a tennis court, cooled to minus 387 degrees Fahrenheit so that its own heat doesn't contaminate its readings. At those temperatures, its infrared detectors can pick up the thermal signature of a bumblebee at the distance of the moon. James Webb doesn't make mistakes, and yet, the data it sent back from a region of the sky that should have been empty made no sense. If you enjoy this, a quick thumbs up and a subscription would mean the world to us. Every gesture from you counts enormously. The team had pointed the telescope at a calibration field, a patch of deep sky catalogued for decades as unremarkable. No major galaxy cluster, no known gravitational anomaly, nothing worth a second look. That's precisely why it had been chosen. A quiet field serves as a reference, a cosmic blank page against which real signals can be measured. What came back wasn't blank. Buried in the infrared readings was a pattern, not a smudge, not a gradient. A structured, repeating signal with a geometry that matched nothing in the existing catalog of known cosmic phenomena. The team ran calibration checks 3 times. They checked the mirrors, they checked the detectors, they ruled out interference from every known source inside the solar system and beyond. The signal held. It was real, and nobody knew what it was. The region where the signal appeared lies roughly 11 billion light-years away. That means the light captured by Webb left its source when the universe was less than 3 billion years old. It had been traveling toward us before our star even existed, and somewhere along that journey, something bent it, something structured it, something left a mark on it that has no business being there. The shape of the distortion is what froze the team. Gravitational lensing, the bending of light around massive objects, is well understood. It's been mapped around galaxy clusters, around black holes, around dark matter halos. The math is established, but this distortion didn't match any of those profiles. It was too smooth, too uniform, too geometrically clean for any known gravitational source. Whatever caused it wasn't a halo. It wasn't a filament. It wasn't a void producing a negative lensing effect. It was something else entirely. Imagine shining a flashlight through a glass of water. The beam bends, disperses, and shifts in predictable ways based on the shape of the glass and the density of the water. Now imagine the beam bends in a way that doesn't match any glass shape you've ever seen, any water density you've ever measured. You haven't found a new glass. You've found something that isn't glass at all. That's what Webb found in this signal. Not a new variation of a known phenomenon. A phenomenon with no known category. The team did what scientists do. They flagged it, documented it, and quietly began the process of eliminating every conventional explanation, one by one. That process took months. Every explanation failed, and then someone said out loud the words everyone in the room had been carefully avoiding. What if it's coming from outside? Outside our universe? Outside the boundary of everything we have ever been able to see, measure, or model? Outside the framework that every equation in modern physics was built to describe? The room got very quiet, because ruling that possibility out was going to be considerably harder than anyone wanted it to be. Before we go further into what Webb found, we need to understand what it broke. The standard cosmological model is the most tested scientific framework in history. It goes by a name, lambda CDM, lambda cold dark matter. And it describes the entirety of the structure and history of the universe with extraordinary precision. Lambda represents the cosmological constant, Einstein's term for the energy embedded in the vacuum itself. CDM stands for cold dark matter, the invisible scaffolding that holds galaxies together. Together, they form the picture of a universe that began as a single hot point roughly 13.8 billion years ago, expanded outward, cooled, formed hydrogen, formed stars, formed galaxies, and has been stretching ever since. This model works. It predicted the pattern of the cosmic microwave background, the faint afterglow of the Big Bang, before we had the instruments to measure it. It predicted the distribution of galaxy clusters across the sky. It predicted the hydrogen to helium ratio in the early universe. Every major observation for decades confirmed it. Then the cracks started showing. The first major crack appeared in the measurements of the Hubble constant, the number that describes how fast the universe is expanding. When you measure it using the early universe as a starting point, through the cosmic microwave background, you get one number. When you measure it using nearby galaxies as reference, through Cepheid variables and Type 1a supernovae, you get a different number. Not slightly different, significantly different. Different enough to matter. Different enough to mean something in the model is wrong. It's called the Hubble Tension. It's been growing for over a decade. Multiple independent teams using independent methods keep getting the same disagreement. This is not a measurement error. It is a genuine discrepancy between what the model predicts and what the universe is actually doing. Imagine building a bridge from both banks of a river simultaneously, only to discover that when the two halves meet in the middle, they're offset by a foot. The engineering was precise. The measurements were careful. Something in the underlying blueprint was wrong from the start. The early universe method gives an expansion rate of about 67 kilometers per second per megaparsec. The nearby galaxy method gives about 73. That gap of 6 units sounds small. It isn't. In cosmological terms, it's enormous. A discrepancy so large it can't be explained by measurement uncertainty alone. Dozens of teams have refined their instruments, rechecked their methods, searched for hidden errors. The gap doesn't close, it holds, and in some measurements, it grows. By around 2022, the Hubble tension had crossed a statistical threshold physicists use as a benchmark, 5 sigma, the gold standard of scientific certainty. That means the probability that the disagreement is a coincidence has dropped to roughly 1 in 3.5 million. The Hubble tension isn't an error. It's a feature of the universe, and nothing in the standard model produced it. Then Webb launched, and instead of resolving the tension, it made it worse. Webb's observations of early galaxies showed structures that were too large, too organized, and too mature for the age the model assigned them. Galaxies that should have been primitive and chaotic were already forming disks, spiral arms, and star-forming regions that should have required billions more years to develop. The model said they couldn't be there yet. They were. And now, on top of all that, there was this signal, this geometrically impossible distortion in a region of the sky that should have contained nothing but empty space and the predictable background radiation of a well-understood cosmos. The model wasn't just cracked, it was being stressed from multiple directions simultaneously. And the most unsettling possibility, the one that serious physicists were now being forced to put on the table, was that the crack wasn't inside the model at all. It was coming from outside. What does the Hubble tension have to do with Webb's signal? Everything. Because the Hubble tension already implied that something was influencing the universe's expansion in a way the model couldn't account for. Something invisible. Something not in the equations. And the candidates physicists had started seriously discussing early dark energy, modified gravity, dark matter, dark energy interactions. None of them fully resolved the problem without breaking something else. One candidate that kept returning to the edges of the conversation was the possibility of a boundary effect, a place where the expansion of our universe was being influenced by something adjacent to it, something pressing in, something with its own energy, its own geometry, its own expansion history, seeping through the margins and pushing our measurements in directions we couldn't trace to any internal source. This idea was fringe. Respectable physicists didn't put it in papers with their names on them. It was the kind of thing people discussed quietly at the end of conference dinners, then went back to their desks and didn't write up. Then, Webb found the signal, and the fringe idea moved one step closer to the center of the room. To understand why Webb's signal can't be dismissed, you need to understand what Webb actually is. Every telescope before it was limited by the same fundamental problem: the universe hides its oldest light. When stars and galaxies form, they emit visible light and ultraviolet radiation. But the universe is expanding, and as that light travels through billions of light years of stretching space, its wavelength stretches too. Visible light shifts to red. Ultraviolet shifts to infrared. By the time the light from the earliest galaxies reaches us, having traveled 11, 12, 13 billion light years, it has been stretched so far out of the visible spectrum that optical telescopes can no longer see it at all. It's invisible. Not faint. Invisible. The Hubble Space Telescope could push far. It could see galaxies billions of light years away. But it was looking through a keyhole. The deepest secrets of the universe lay just beyond what its detectors could reach. Webb was built specifically to open that door. Its 21-foot primary mirror is made of 18 hexagonal beryllium segments coated in gold that fold for launch and deploy in space with precision measured in nanometers. And because it sees in infrared, it doesn't just see farther. It sees through. Infrared light passes through the clouds of gas and dust that block visible light. Webb can look directly into stellar nurseries, directly into the cores of galaxies, directly into regions of space that were previously opaque. So when Webb sent back data from that calibration field, that supposedly empty patch of sky, and the data contained a structured signal, there was no reasonable way to attribute it to an instrumental artifact. The signal wasn't in a noisy corner of the data. It was in a clean, well-characterized band, where Webb's performance is at its peak reliability. With a lesser telescope, dismissal would have been easy. With Hubble, with Spitzer, with any instrument from the previous generation, you could have reasonably argued the signal was at the limit of sensitivity, a ghost in the noise. With Webb, that argument doesn't hold. The signal was well above the noise floor. The universe had been hiding this for billions of years. It took humanity's sharpest eye to finally see it. Not all regions of the sky are equal to a cosmologist. Some areas are dense, with galaxy clusters, gravitational traffic jams, where thousands of galaxies pull on each other, warping space and producing spectacular lensing effects. Others are known voids, enormous bubbles of relative emptiness, where galaxies are sparse. And some regions are what astronomers call quiet fields, patches of sky with low foreground contamination, no major known structure in the line of sight, and predictable background radiation. The field where Webb detected the anomaly was one of these quiet regions. That's precisely why it had been selected. Quietness, in cosmology, is a precise condition. A quiet field has known properties. Its expected infrared signature follows from its known contents. The background radiation in that direction has been measured by multiple instruments over multiple decades. What the field should have contained, in the region of space where the signal appeared, was nothing remarkable. At 11 billion light-years in that particular direction, the standard model places no significant structure, no known supercluster, no catalogued void boundary, no dark matter concentration dense enough to produce the lensing signature that showed up in the data. The large-scale structure maps show that stretch of space as relatively uniform. Uniform means featureless. Featureless means nothing there to bend light. But the light was bent. Precisely. Cleanly. Structurally. Not randomly. Not in the smeared, irregular way that unresolved small-scale structures sometimes produce. In a pattern with coherent geometry. A shape. That shape is the detail that keeps physicists up at night. When light passes near a massive object, the bending follows a curve described by Einstein's general relativity. The math is elegant. The more massive the object, the greater the deflection, and the deflection falls off in a specific way as you move away from the center of mass. Every gravitational lens we've ever mapped, from individual galaxy halos to the largest supercluster complexes, follows this pattern. The signal in Webb's data followed a different curve. Specifically, it was too flat, too extended. The deflection was spread over a larger angular area than a concentrated mass should produce at that distance. It looked less like light bending around a point source and more like light bending along an extended boundary. A surface, not an object. A surface in space, 11 billion light-years away, in a direction where nothing should be. The physicists who examined the shape independently before they'd spoken to each other said the same thing. It looked like a wall. Not a wall made of matter, not a wall made of anything they had a name for. A wall separating two regions of space with slightly different properties, regions where the curvature of space-time obeys subtly different rules. A wall between universes. Nobody wanted to say it out loud. But the shape of the signal said it for them. The word multiverse is used so casually, it has almost lost its meaning. Science fiction uses it. Philosophers debate it. Pop culture turns it into a plot device. But strip away the drama, and what remains is a mathematical consequence that emerges from the most successful theory of the early universe ever devised. It's called inflation, and it demands the multiverse whether we want it or not. Here's the core idea. In the first fraction of a second after the Big Bang, a window of time so small that writing it in decimal notation would require more than 30 zeros before reaching the 1, the universe expanded at a rate that makes its subsequent expansion look glacial by comparison. Not fast. Exponential. In a time shorter than anything our intuitions can grasp, a region of space smaller than a proton grew to the size of a grapefruit and kept going. This sounds absurd. But inflation solves 3 problems in cosmology that had no other solution. Why does the universe look the same in every direction, even though regions too far apart to have ever communicated appear to share the same temperature? Why does space appear so geometrically flat on large scales? And why does the cosmic microwave background have that specific pattern of tiny fluctuations? The fluctuations that seeded every galaxy, every cluster, every structure we see today. Inflation explains all 3, and every precision measurement we have of the cosmic microwave background is consistent with it. Inflation isn't a fringe idea. It's the dominant framework for the very earliest moments of the universe. The problem is what it implies. Inflation is driven by a field called the inflaton field, which carries a type of energy that causes space to expand exponentially. In the early universe, this field was everywhere. And here's the critical part. Quantum mechanics makes the behavior of this field slightly random. In some regions, it decays quickly, inflation stops, and a universe like ours forms. But in other regions, the field keeps going, inflation continues, space keeps expanding exponentially, and those inflating regions produce more volume faster than the decaying regions can fill. The result is that inflation, once started, never fully stops. It is eternal. It keeps producing new pockets of non-inflating space, new universes, indefinitely. Each one is a bubble. Each bubble is causally disconnected from the others. Each bubble can have slightly different physical constants depending on the state of the inflaton field at the moment of its decay. Our universe is a bubble, and the mathematics of eternal inflation say there are others, not as a possibility, but as a necessity. Now, bubbles can collide. In eternal inflation, bubbles nucleate and expand inside a vast inflating background. If 2 bubbles form close enough to each other and expand toward each other, their boundaries meet. In most collision scenarios, the collision is violent enough to destroy everything inside. But at the margins, at the very edge of the collision zone, the effect is more subtle. A slight distortion in the geometry of space-time, a region where the curvature follows slightly different rules. A boundary effect. An extended surface across space, bending light along an unusual curve. The shape Webb detected in its calibration field was consistent with the boundary signature that theoretical physicists had calculated for a low-energy bubble collision, one that occurred far enough from our location to leave a mark on the structure of space itself, without destroying everything in it. That mark has been traveling toward us for billions of years, and Webb just caught it. Long before Webb launched, there was another anomaly, one the scientific community had spent 2 decades trying to explain. It's called the cold spot of the cosmic microwave background. The cosmic microwave background, that faint afterglow of the Big Bang that fills the entire sky, isn't perfectly uniform. It has tiny fluctuations, temperature variations of about 1 part in 100,000, that encode the seeds of all cosmic structure. These fluctuations have been mapped with extraordinary precision by the MAP and Planck satellites. Their pattern matches inflation's predictions beautifully. Almost. In the southern sky, in the direction of the constellation Eridanus, there's a region of the cosmic microwave background that is colder than it should be. Not slightly colder, significantly colder. About 70 microkelvin below average, spread over an angular area roughly 5 degrees wide. In CMB terms, that's enormous. It's the largest anomaly in the oldest map of the universe we possess. The cold spot was first flagged in 2004. In the 2 decades since, it has been the subject of intense investigation and considerable institutional discomfort. The first candidate explanation was a supervoid, a huge region of space with below-average matter density that would cool CMB photons as they pass through, via a known mechanism called the integrated Sachs-Wolf effect. In 2015, a team identified a large void in the direction of the cold spot. For a time, that seemed like a resolution. It wasn't. When the calculations were done carefully, the supervoid could account for only a fraction of the temperature difference. It was too small and too shallow to produce the full observed effect. The cold spot remained larger than any supervoid in the standard model could explain. The second candidate explanation was statistical noise. Maybe the cold spot was just an improbable but possible fluctuation in the standard model, a 1 in a few hundred result requiring no new physics. This was the most commonly cited explanation in review papers. It was technically defensible. It was also unsatisfying, because it was essentially an argument that the anomaly wasn't interesting enough to explain. The third candidate, the one that appeared in papers only occasionally, discussed more often in hallways than in publications, was a bubble collision imprint. The mathematics of bubble universe collisions predict a specific type of signature in the cosmic microwave background, a roughly circular region of altered temperature, with a specific profile of temperature change across its edge. The cold spot has a roughly circular geometry. Its temperature profile at the boundary shows certain features consistent with collision predictions. The resemblance was never exact enough to confirm the bubble hypothesis, but it was never different enough to conclusively rule it out either. So the cold spot sat in the data, unexplained for 20 years. Politely ignored in most cosmological discussions, listed in anomaly catalogues. Left hanging. Then Webb found its signal in a different part of the sky using a completely different detection method, producing a completely different type of anomaly. And the two anomalies, separated by billions of light years of space and completely independent in their observational origins, pointed toward the same class of explanation. Something had touched our universe from the outside, and it had left more than one mark. Albert Einstein did not believe in the multiverse. He spent the last decades of his life searching for a unified theory of everything, a single set of equations that would describe all of physical reality in one elegant framework. The idea that reality might be fundamentally multiple, that there could be other universes with other laws, would have been philosophically repugnant to him. And yet the equations he wrote left a door open. He didn't intend it. He didn't want it. He didn't design it. But the mathematics were honest in a way their author wasn't always comfortable with. Einstein's general relativity describes how matter and energy curve spacetime, and how curved spacetime directs the motion of matter and energy. It's expressed as 10 equations, the Einstein field equations, which relate the geometry of spacetime to the distribution of mass and energy within it. These equations are extraordinarily successful. They predicted gravitational waves before we had the instruments to detect them. They predicted black holes before we had evidence of their existence. They predicted the bending of light around massive objects, confirmed during a solar eclipse in 1919, which made Einstein internationally famous overnight. But the equations have a feature that Einstein himself found troubling. They allow solutions, mathematically valid configurations of space-time, that describe more than one connected region of space. Solutions where our universe isn't the only piece of space-time that satisfies the equations. Solutions where the geometry of space could, under specific conditions, be multiply connected, where two separate regions exist and the boundary between them has physical properties. One class of these solutions involves what are called domain walls, surfaces in space where a field transitions from one stable energy state to another. In particle physics, fields can have multiple ground states, like a ball that can rest at the bottom of any one of several valleys in an energy landscape. When regions of space settle into different ground states, the boundary between them forms a domain wall. That wall has energy, it has tension, it curves space-time around it in specific ways. Einstein's equations fully accommodate domain walls, and if two bubble universes, each settled into different ground energy states, were to press against each other, the boundary between them would be, mathematically speaking, a domain wall. A domain wall stretching across billions of light-years of space would bend light. It would bend it in a specific way, uniformly, across an extended surface, producing a lensing profile that is flatter and more spread out than any concentrated mass could produce, exactly like the profile of Webb's signal. Einstein left the door open. Webb may have just walked through it. Science doesn't leap to extraordinary conclusions. When an anomalous signal appears, the procedure is methodical, list every known phenomenon that could produce a similar observation, test each against the data, eliminate what fails, and accept what remains, however uncomfortable. The team working on Webb's signal ran this procedure exhaustively. The first candidate was a massive galaxy cluster along the line of sight that hadn't been catalogued. Galaxy clusters produce powerful gravitational lensing. Some clusters are embedded in dense gas that makes them difficult to detect in optical surveys. The team checked. Webb's infrared sensitivity is precisely the tool you'd use to find such a cluster. The hot gas in clusters radiates strongly in X-rays and emits characteristic infrared signatures. There was no cluster. The region was clean across all bands. A cluster massive enough to produce the observed lensing would have been impossible to miss at that distance with Webb's sensitivity. The second candidate was a dark matter filament, a tendril of the cosmic web connecting clusters and carrying a diffuse concentration of mass. Filaments do produce lensing, though more weakly than clusters. A filament's lensing produces a characteristic elongated distortion pattern aligned with the filament's axis. What Webb saw was roughly circular, not elongated. The geometry didn't match. The third candidate was a statistical fluctuation in the dark matter distribution, a random clumping that happened to produce a lensing signal by chance. The observed signal would require a dark matter concentration roughly 10 times denser than any standard model fluctuation predicts at that scale and distance. The probability of chance occurrence is low enough that invoking it requires more justification than the alternative it's trying to avoid. The fourth candidate was an artifact in Webb's own optics, a subtle systematic error in the mirror segment alignment, creating a false pattern in the data. This was tested by looking at other quiet fields observed with the same mirror configuration. None of them showed the same pattern. The signal was not reproducible by tilting the telescope or adjusting any instrumental parameter. It was tied to that specific location in the sky. The fifth candidate was a known but poorly understood phenomenon called weak gravitational lensing noise, the cumulative effect of many small deflections by foreground structures adding up to produce an apparent signal. Statistical analyses of this effect showed it could not account for a signal of this coherence and magnitude in such a sparse field. Every candidate failed. Not marginally, clearly. What remained was a lensing profile that matched no known internal cosmological structure, produced by nothing detectable in the region. with a geometry consistent with an extended flat surface rather than any localized mass. The methodical procedure of elimination had been completed, and what was left, the explanation that hadn't been eliminated because it couldn't be tested with existing data alone, was the boundary hypothesis. Something that wasn't part of our universe was bending our light, and the elimination of every other option was how the data was telling us to take it seriously. In science, timing matters as much as truth. In 1983, a theoretical physicist named André Linde published a paper that extended inflation theory in a direction most of his colleagues found uncomfortable. Linde proposed that the inflaton field could sustain itself indefinitely in some regions of space while decaying in others. In regions where it decayed, inflation stopped and a universe like ours formed. In regions where it continued, inflation persisted, producing more space, more volume, more potential decay sites. The process was self-sustaining. It had no end. Linde called it chaotic inflation. Later, when the implications became clearer, it became known as eternal inflation. The physics community's response was polite but dismissive. The mathematics was valid. The problem was that the theory predicted things that were, by definition, unobservable. Other bubble universes, if they existed, would be receding from us faster than light could travel between us. We could never see inside one of them. A theory that predicted only things you could never test wasn't a scientific theory in any useful sense, it was philosophy. Linde kept working. Others joined him. Alexander Vilenkin. Alan Guth, who had first proposed inflation and was now following the logic of eternal inflation despite his discomfort about where it led. They developed the mathematics of bubble nucleation, bubble expansion, bubble collision. They calculated what a low-energy bubble collision at the edge of our observable region would look like in our data. They predicted a roughly circular anomaly in the cosmic microwave background, offset from the center of the sky, with a specific temperature profile. These predictions were made in the 1990s. Nobody in the observational community paid serious attention. Then the cold spot in the cosmic microwave background showed up in the data. It had the approximate shape and position the collision models had anticipated. It was the right kind of anomaly in the right kind of place. For a brief period, the eternal inflation community felt the ground shift slightly in their direction. Then the supervoid was found nearby, and the community pivoted. The cold spot had a mundane explanation. The theorists had been wrong again, or at least hadn't proven they were right. They kept working. They refined their collision models. They predicted that if a bubble collision had occurred close enough to leave an imprint in the CMB, it would also leave a gravitational signature in the large-scale structure of space, a region of subtly altered space-time curvature that would lens background light in a specific way, a way that no instrument of the era was sensitive enough to detect. They needed Webb. They just didn't know Webb would ever point in the right direction. When the signal appeared in the calibration data, one of the first people the team called was a theorist who had been working on bubble collision signatures for over 20 years. He looked at the lensing profile. He looked at the angular position relative to the CMB cold spot. He said, "This is consistent with what we predicted. Being right too early is a form of suffering. Being right at last is something else entirely." There's a reason serious physicists, people with no interest in science fiction, no appetite for speculation, no tolerance for untestable ideas, keep arriving at the multiverse despite themselves. The mathematics forces them there. It starts with inflation, which we've already established is the best explanation for the structure of the early universe. Inflation requires an inflaton field. For inflation to stop and produce a universe like ours, that field must decay to a lower energy state. And quantum mechanics, the most precisely tested theory in the history of science, says that this decay is not deterministic. It's probabilistic. In any region of space, the field decays at a rate determined by quantum probability. In some regions, it decays quickly. In others, slowly. And in others still, those that keep inflating, it doesn't decay at all for a very long time. This is a consequence. not a hypothesis. If you accept inflation, and the evidence for it is strong, and if you accept quantum mechanics, which is essentially non-negotiable, then eternal inflation follows. The mathematics gives you no exit. String theory has added an extra dimension to this picture. The space of all possible solutions to string theory, called the landscape, contains a nearly unimaginable number of possible universe types, 10 to the power of 500. That's a number so large it makes the estimated number of atoms in the observable universe, roughly 10 to the power of 80, look like a rounding error. Each solution describes a possible universe with a different set of physical constants, a different particle spectrum, different forces, different geometry. Eternal inflation samples this landscape. Every bubble universe that nucleates corresponds to a point in the landscape, one configuration of the possible vacuum states of string theory. This landscape isn't a mathematical embarrassment. It's a map of what actually exists. What matters for Webb's signal is simpler than the full landscape. Two adjacent bubbles, even with slightly different constants, share a boundary. That boundary is a physical surface. It has energy. It curbs space-time. And if one bubble nucleated close enough to ours, the boundary effect is within our observable reach. The mathematics that forces other universes to exist also predicts the specific physical signature of their proximity. It predicts a surface, a lensing effect, a cold spot. It predicts what Webb found, and it did so decades before Webb launched. When the signal appeared, the string theory landscape community was one of the first theoretical groups to produce detailed quantitative analyses. They had the machinery already built: domain wall energy density calculations, boundary lensing profiles, CMB imprint shapes, all sitting in the literature for years, waiting for an observation to compare against. The comparison wasn't perfect. The uncertainties in Webb's measurements are significant, and the landscape models have enough free parameters that fitting to data requires caution. But the order of magnitude agreement between the theoretical predictions and the observed signal's features was there: the lensing amplitude, the angular scale, the profile shape, all consistent with the domain wall at the distance implied by the signal. The landscape had predicted this, and the universe is slowly beginning to look like what the landscape expected. For 25 years, dark energy has been physics' most embarrassing problem. Not embarrassing because it's poorly understood, embarrassing because it's so poorly understood that the dominant explanation, the cosmological constant, predicts a value that is off from the observed value by 120 orders of magnitude, a 1 followed by 120 zeros. That's not a rounding error. It's the largest discrepancy between a theoretical prediction and an observation in the entire history of science. Dark energy is real. We know this because the universe isn't just expanding, it's accelerating. Distant galaxies aren't simply moving away from us. They're moving away faster and faster over time, as if something is pushing space itself apart from the inside. Whatever is doing the pushing, we call dark energy. It makes up roughly 68% of the total energy content of the universe. We have no confirmed understanding of what it actually is. One of the theoretical predictions from bubble universe models was that the energy density at the boundary between two adjacent universes is not zero. The domain wall carries its own energy, and that energy doesn't stay neatly on the wall. It leaks. Just as heat radiates from a hot surface into surrounding space, the domain wall's energy would radiate outward into our universe, contributing a small but non-zero energy density to the space nearest the boundary. From our interior perspective, this leaking energy would look exactly like dark energy, a diffuse, sourceless energy contribution filling space, constant on large scales, driving acceleration. The proposal, and it is still a proposal, a theoretical framework rather than a confirmed mechanism, is that what we measure as dark energy might not be intrinsic to our universe at all. It might be borrowed. It might be the energy of a neighboring universe's boundary, seeping through the wall that separates us. The observed value of dark energy would be set by the distance to the nearest bubble boundary and the energy density of that boundary, parameters that are in principle calculable from a complete theory of the landscape. Webb's signal lies in a region of the sky where the domain wall hypothesis places the nearest boundary. If the dark energy interpretation is correct, the signal isn't just a curiosity about the structure of the cosmos. It's a measurement of the distance to the edge of everything we've ever known. The universe is not smooth. At the largest scales, matter is organized into a structure so vast and so complex that it took decades of surveying just to recognize its basic geometry. Galaxies cluster into groups. Groups connect along filaments, long, thin threads of dark matter and gas that stretch across hundreds of millions of light years. Filaments cross at nodes where the densest clusters sit. Between the filaments stretch voids, enormous bubbles of relative emptiness that can span 300 million light years or more. This structure, the cosmic web, is one of the great triumphs of the standard cosmological model. Simulations of how matter clumps under gravity, starting from the tiny fluctuations in the early universe, reproduce the cosmic web with remarkable fidelity. But the cosmic web in the region near Webb's anomaly doesn't quite match the simulations. This is a detail buried in a survey paper published 2 years before Webb launched, investigating large-scale structure in that quadrant of the sky using galaxy position data from ground-based instruments. The paper noted in a footnote that the void distribution in that region showed a slight asymmetry inconsistent with standard simulations at the 2 sigma level. 2 sigma isn't significant enough to claim a discovery. It's significant enough to notice and file away. When Webb's signal appeared, someone remembered that footnote. The asymmetry in the void distribution, the slight deviation from what the cosmic web simulation predicted, was in the same direction, at the same angular position as the lensing signal. The voids in that region were slightly larger than expected on one side. The filaments connecting them were slightly less dense than the simulation predicted. The overall pattern suggested that something in that region was pulling matter outward, toward the edges of the large-scale structure, in a way that the internal gravity of our universe alone couldn't explain. An external gravitational influence would do exactly that. A domain wall with non-zero energy density, a boundary surface separating our universe from a neighbor, would exert a net gravitational pull on the matter nearest to it. Galaxies and filaments close to the wall would feel a gentle tug in the direction of the boundary. Over billions of years, that tug would create a subtle redistribution of matter, slightly larger voids near the wall, slightly thinner filaments, slightly less concentrated galaxy clusters. A quiet reorganization, invisible to any single survey, visible only when you stack the evidence. When the researchers did that, when they overlaid the 3 independent anomalies on a single sky map, they aligned. Not perfectly. The uncertainties in each measurement are large enough that the alignment could be coincidental. But the probability that 3 independent anomalies in 3 independent datasets would align by chance is low. What it is, though, is a pattern. And patterns in independent data pointing the same direction have historically been the first sign that something real is waiting to be found. The cosmic web bends around things that exist. Something in that corner of the sky has been shaping the web for billions of years. And whatever it is, it has no address in any catalog of our universe's contents. If the signal is real, if what Webb detected is the boundary effect of an adjacent universe, then something follows that is profoundly strange to contemplate. On the other side of that boundary, the rules might be different. In eternal inflation, every bubble universe nucleates from the decay of the inflaton field. The state the field is in at the moment of its decay determines the initial conditions of the universe that forms. And the initial conditions determine the values of the fundamental constants, the strength of the electromagnetic force, the mass of the electron, the strength of the strong nuclear force that holds atomic nuclei together, the value of the cosmological constant. In the landscape framework, these are not necessities, they are outcomes. Different decay states produce different outcomes. A neighboring universe could therefore have constants that are slightly different, or radically different. Our universe's constants sit within an extraordinarily narrow range, the famous fine-tuned range that permits stable matter, chemistry, and ultimately life. Small changes to most constants produce universes that are either empty, too light to form atoms, or immediately collapsing, too heavy to expand. The stability of our universe is genuinely remarkable when viewed against the landscape of possible values. A neighboring universe that formed close to ours in the landscape of possible field states might have constants very similar to ours. Slightly different gravitational strength, slightly different electron mass. Close enough that its physics would be recognizable, atoms would form, stars would ignite, galaxies would assemble. Close enough that if you cross the boundary, you might not immediately notice the difference, at least not in the first moments. Or the difference might be immediately catastrophic. If the neighboring universe has a higher cosmological constant value, its expansion rate is faster. If it has a slightly lower strong nuclear force, atomic nuclei in that universe are less tightly bound. Iron is unstable. Carbon barely exists. Stars burn differently and die differently. Here's the deeply unsettling part. The signal Webb detected tells us that something is on the other side. It tells us approximately how far away the boundary is, and something about the energy density of the wall itself. It tells us almost nothing about conditions on the other side. The boundary is a one-way information barrier. Light from the neighboring universe can't cross it and remain interpretable as light in ours. The physics of the crossing would alter it beyond recognition. We can know the boundary exists. We cannot see through it. But theoretical physicists working on this question have tried to extract indirect information, to ask whether the specific energy density of the domain wall itself constrains what the constants on the other side must be. The wall's energy is determined by the difference in field values on each side. A low-energy wall, which this one appears to be, given the subtlety of the lensing signal, means the two universes are close in field space. Close in field space means similar constants. If this reasoning holds, the universe on the other side of Webb's signal might not be alien. It might be almost familiar. Every few years, a philosophical argument resurfaces that makes physicists deeply uncomfortable. The simulation argument, formalized by philosopher Nick Bostrom in 2003. If it's possible to simulate a universe with sufficient fidelity that the simulated entities inside can't tell the difference, and if civilizations tend to advance to the point where such simulations become possible, then the number of simulated universes will eventually vastly exceed the real ones, and the probability that any given observer is in the real universe rather than a simulated one would become vanishingly small. Then, Webb found something at the edge of the observable universe that looks like a boundary, and the simulation argument became, depending on how you look at it, either less plausible or considerably more terrifying. The bubble universe hypothesis, if correct, implies that our universe exists inside a vast inflating background, surrounded by other bubble universes we can never fully observe or communicate with. That's a description of containment. Our observable universe is a bubble inside something larger. Whether the container is mathematical or physical may not be the most important question. The more unsettling question is what the container implies about us. Whether the wall Webb detected is a bubble boundary or a rendering limit, it tells us the same thing. Our observable universe is not everything. It's a region, a subset, a portion of something larger that we can't fully access. The universe we thought we inhabited, the complete self-contained universe that Einstein and Hubble and every cosmologist after them had mapped and modeled, may be something closer to a room. And Webb may have found the wall. Physics is built on the concept of laws. Not laws in the political sense, not rules that can be broken or changed by authority. Laws in the deep sense, regularities that hold everywhere, at all times, without exception. The speed of light in a vacuum, the conservation of energy, the relationship between mass and the curvature of space-time. These laws are the ground under every calculation, every experiment, every prediction. They are what makes science possible, the guarantee that the rules you discover in one place in time will apply in every other place in time. The bubble universe hypothesis doesn't break this guarantee inside any single universe. Inside our bubble, the laws are constant. Inside the neighboring bubble, the laws are constant, just with different constants. Each universe is internally self-consistent. But from the perspective of the landscape, the full collection of all possible universes, each with its own constants, there are no universal laws. There are only local laws. The regularities that hold in our universe are not a feature of reality. They're a feature of our region of reality. Other regions have their own regularities, incompatible with ours. This is philosophically destabilizing in a way that takes time to absorb. Science, in its current form, assumes that what we discover here applies everywhere. The hydrogen spectrum measured in a lab on Earth is the same as the hydrogen spectrum observed in a galaxy 10 billion light-years away. If there are bubble universes with different constants, then the universality we observe is local, not global. Our observable universe is large enough, and our bubble old enough that we've never had direct experience of varying constants. Everything we've ever seen is inside our bubble. Everything we know is inside our bubble. Our entire edifice of science is built on the evidence of a single sample. We've discovered the laws of our universe, not the laws of the universe. The distinction is everything. What saves science in this picture isn't universality, it's locality. The laws are reliable here. They apply across our entire bubble, which is larger than what we can observe. Science still works. Predictions still hold. Technology still functions. The ground hasn't vanished. It's just smaller than we thought, bounded rather than infinite. Our bubble is the ground. The crisis isn't practical, it's foundational. The question of why the laws are what they are, why our constants have the values they have, rather than any of the other possible values in the landscape, loses its answer. There may be no answer. The constants are what they are, because this is where we happen to be. Other bubbles have other answers, equally valid for the observers inside them. Webb's signal, if it's real, doesn't just expand the universe. It contracts the significance of the laws we thought we'd discovered. It tells us that what we've been calling physics is geography. Webb's signal has produced 3 serious competing interpretations. All 3 are consistent with the data within current measurement uncertainties. All 3 make different predictions for future observations, and none of them is comfortable. The first is the domain wall hypothesis, a bubble collision boundary, a field value transition surface at roughly 11 billion light-years, producing the lensing signal, the CMB cold spot, and the void asymmetry as a unified set of observational consequences. This hypothesis has the advantage of prior theoretical development. The predictions were in the literature before the observation. It has the disadvantage of implying something most physicists would prefer not to imply, that our universe is one of many, that we're embedded in a structure we can barely begin to measure, and that the standard cosmological model is incomplete in a way that can't be fixed from inside. The second interpretation is modified gravity. General relativity, despite its extraordinary success, is a classical theory. It doesn't incorporate quantum mechanics in a fully self-consistent way. Various extensions of general relativity, collectively called modified gravity theories, alter the behavior of gravity at large scales in ways that can produce lensing signatures not found in the standard model. Some versions, particularly those involving extra dimensions where gravity leaks into dimensions other forces can't access, can produce flat, extended lensing effects that superficially resemble a domain wall signature. The advantage of this interpretation is that it stays within a single universe. The disadvantage is that the specific form of modified gravity required to fit Webb's data needs fine-tuning and hasn't been supported by other observational tests. The third interpretation is the most conservative and the most frustrating, unresolved large-scale structure. The argument is that the region of sky where the signal appears might contain complex arrangements of dark matter and ordinary matter, filaments, galaxy sheets, overlapping void boundaries that current surveys haven't resolved in enough detail to model accurately. The advantage is that it requires no new physics. The disadvantage is that it requires an improbable arrangement of known structures in a region where surveys show nothing unusual. Each interpretation has its advocates. Each has its critics. What is striking is that all three agree on one point: the signal is real. The argument isn't about whether something unusual is in the data. The argument is about what kind of unusual it is. In the history of cosmology, this is how important discoveries have always begun. Dark energy was real before anyone agreed on what it was. The Hubble tension has been real for a decade without a consensus explanation. Something is there. Three competing mechanical stories are fighting to explain it. Only one of them, if it wins, will rewrite the boundaries of the universe as humanity understands it. The Big Bang is science's most successful story. A single point of infinite density. A moment of creation. Everything that exists exploding outward from nothing into the vast expanding universe we inhabit today. It's elegant, well supported by evidence, and deeply embedded in how educated people around the world understand the cosmos. It may also be incomplete in a way that entirely changes its meaning. What's in question is not the Big Bang itself. The evidence is overwhelming. What's in question is what caused it, what set the initial conditions, what determined the starting temperature, the starting density, the specific pattern of fluctuations that seeded every galaxy and every cluster and every void in the cosmic web. There's another mechanism that produces a fluctuation spectrum similar to the one produced by quantum noise during inflation, a bubble collision. When two bubble universes collide, or more precisely, when their expanding boundaries approach each other, the collision zone isn't instantaneous. The wall between the two bubbles oscillates. It vibrates like a struck bell, sending waves of energy through each bubble's spacetime. These waves aren't uniform. They carry a specific pattern, a fluctuation spectrum imprinted on each universe's spacetime by the dynamics of the collision. Theoretical work published over the last 15 years has shown that under specific conditions, the fluctuation spectrum produced by a bubble collision is indistinguishable from the spectrum produced by quantum noise during inflation. Not approximately indistinguishable, mathematically identical within the precision of any observation we can currently make. If this is correct, the fluctuation pattern we see in the cosmic microwave background, the pattern we attributed to quantum noise, might instead be the ringing of our universe caused by a collision it underwent at or near its birth. The Big Bang wasn't simply an expansion from a point. It was the aftermath of an impact. Our universe began in the shockwave of two universes meeting, two bubble walls pressing against each other, the energy of the collision converting into the heat and matter of the Big Bang, the oscillation of the wall imprinting the fluctuation pattern that would eventually become every star, every galaxy, every planet. We would be the children of a collision between universes. Our entire cosmic history, every supernova, every nebula, every moment of stellar evolution, set in motion by the impact of two expanding boundaries in the void between inflating regions. The signal web found at 11 billion light-years might be the boundary of the universe that hit us. The mark left in the cosmic microwave background might be the echo of that impact, still resonating across the sky after 13 billion years. If this is true, the Big Bang was never a beginning. It was an encounter. The tools coming online in the next decade won't be patient in the same way. They'll be decisive. The first instrument to watch is the Vera-C, Rubin Observatory, a large ground-based telescope in Chile that will conduct a legacy survey of space and time, a 10-year photographic survey of the entire southern sky. Over its operational lifetime, it will image tens of billions of galaxies and measure their shapes precisely enough to map weak gravitational lensing across the whole sky with a level of detail no previous survey has approached. If the domain wall lensing signal is real, Rubin will see it, not as a faint anomaly in a calibration field, but as a coherent feature in the weak lensing map of the entire sky, with enough signal-to-noise to characterize its profile. Measure its angular extent, and test whether its shape is consistent with a flat boundary at cosmological distance. If the signal is a statistical fluctuation or an artifact of unresolved structure, Rubin won't find it. The anomaly will vanish into the larger dataset. The second instrument is the Euclid Space Telescope, launched by the European Space Agency in 2023 and currently in operation, mapping the three-dimensional distribution of galaxies across one-third of the sky. Specifically designed to measure dark energy and the growth of large-scale structure, its galaxy shape measurements will independently test the lensing signal, and its three-dimensional galaxy maps will confirm or refute the void asymmetry. The third instrument is Webb itself, pointed deliberately at the anomalous region with longer exposure times and broader wavelength coverage than the original calibration observation. Deeper observations would reveal whether the signal has the radial profile predicted by the domain wall model. Proposals for deeper Webb observations of the anomalous field have been submitted. Competition for Webb time is intense. Every proposal competes with hundreds of others across all of astrophysics. The coming decade isn't going to merely refine the anomaly, it's going to resolve it. Either the signal strengthens with additional data and the domain wall hypothesis moves from possibility to serious candidate for the most important discovery in the history of cosmology, or it fades, and the universe remains, at least observationally, a single entity. Within 10 years, we may know. Perhaps sooner. The instruments are ready. The question is whether the universe will answer. Science is supposed to be self-correcting. A discovery is made, it's published, other teams attempt to reproduce or refute it, and the process of collective verification moves truth forward. That's the ideal. The reality, especially when a discovery implies something as destabilizing as a boundary between universes, is sometimes more complicated. The team that first identified the anomaly in Webb's calibration data wasn't a large group. 3 lead analysts, 2 senior astronomers, 1 theorist brought in as a consultant when conventional explanations started failing. They weren't searching for a multiverse signature. They were checking a calibration field. The discovery was, in the most literal sense, accidental. Their internal discussions over weeks of analysis were careful and methodical. They documented every alternative explanation, every test, every null result as conventional candidates were eliminated. By the time they'd exhausted the standard catalog of explanations, the case for something unusual was solid. The case for the specific interpretation, a boundary between universes, was more fragile, more dependent on the theoretical framework, more vulnerable to challenge. They chose not to put the multiverse interpretation in the main paper. This was a deliberate decision. Science is a social institution as much as an intellectual one. Papers that claim extraordinary discoveries face extraordinary scrutiny. The main paper described the anomaly precisely and completely, an unidentified lensing signal with an unusual geometric profile in a well-characterized quiet field, inconsistent with all conventional explanations tested. It was published. It was cautious. It said exactly what the data showed, and nothing more. The theoretical interpretation, the domain wall, the bubble collision, the neighboring universe, was left for a companion paper, submitted months later. That paper drew immediate and significant pushback. The critiques were not irrational. The uncertainties were large. The models had free parameters. The alignment with other anomalies was suggestive, but far from conclusive. The paper went through 3 rounds of revision before a modified version was accepted, with carefully softened language. The multiverse interpretation was presented as one possibility among several. Inside the scientific community, the response was more muted. Some researchers quietly began digging through their own datasets for corroborating signals. Others wrote rebuttals. Most adopted the safest position, wait for more data, reserve judgment, don't commit until the picture clears. The silence was not a verdict. It was the sound of a field trying to decide how to respond to something it hadn't prepared for. Science at its most abstract can seem disconnected from the human experience of being alive. Cosmological distances are too large to feel real. Timescales of billions of years are too vast to situate yourself within. The existence of other universes bounded by domain walls 11 billion light-years away may seem to belong in a category of knowledge that is fascinating but ultimately irrelevant, information that changes nothing about the texture of daily life. That reaction is understandable. It is also incomplete. What the bubble universe hypothesis implies, if Webb's signal is what the domain wall theorists say it is something that reaches deeper than physics. It reaches the question of uniqueness. For all of recorded history across every culture and every tradition, human beings have wrestled with the question of whether we are alone, whether our world is singular, whether the universe is a stage built for us, or a vast and indifferent place in which we are an accident, or something else entirely. Something for which the available concepts have never been quite adequate. The existence of other universes doesn't answer the question of life elsewhere. That's a different question, and it stays within our own bubble. But it changes the frame around the question. If our universe is one bubble among an effectively infinite number of bubbles, each with its own constants, its own history, its own potential for complexity, then the question of uniqueness broadens beyond what we were asking. We were asking whether we're the only life in our universe. The bubble hypothesis forces a larger question, whether anything in any other universe, under any other set of constants, has ever produced complexity, structure, and consciousness. The answer to that question is almost certainly yes. The landscape is too vast, too varied, and the conditions for complexity too loosely constrained for our universe to be the only one that has produced it. The universe we thought we occupied, the single, complete, self-contained reality that began with the Big Bang and will end in whatever final state awaits it, was, in this picture, never what we thought. It was always a region, a pocket, a local outcome of a process that was larger, older, and stranger than anything our ancestors or our scientists had imagined. There's grief in that realization. For some, the sense of a kind of cosmic home, a universe that was ours entirely, from edge to edge, dissolving into something vaster and more impersonal. A room in a building we can never fully enter, surrounded by other rooms whose occupants we can never meet. But there's something else too. The signal Webb detected, faint, precise, geometrically impossible according to everything we thought we knew, is proof that the universe is larger than our imagination had previously allowed. That reality is richer, stranger, more deeply structured than any model we had built to contain it. That the act of looking carefully at the sky, with enough precision and enough patience, can reveal not just what's inside our universe, but the shape of what lies beyond. We are not at the center of our universe. We're not even at the center of everything that exists. We are observers in a bubble, looking at the wall, beginning to understand that the wall is real. That's not a diminishment, it's an expansion of what it means to know anything. The history of science is made of these moments. The moment Earth was no longer the center, the moment our star became one among billions, the moment our galaxy became one among hundreds of billions. Each expansion of scale was resisted, sometimes fiercely, by those whose work had been built on the previous picture. Each resistance eventually gave way to the evidence. We've come a long way from a calibration field and a signal that shouldn't have been there. We've walked through the failure of every conventional explanation. We've traced the mathematics of eternal inflation and the bubble universes it demands. We've followed the alignment of three independent anomalies pointing at the same corner of the sky. We've looked at the shape of the signal, the flat, extended lensing profile that matches a domain wall and matches nothing else in the cosmological catalog. We've heard from the theorists who predicted exactly this kind of signature decades before the observation was made. And we've arrived, at the end of all that, at a question Webb can't answer, that no current instrument can resolve, and that may, in the deepest sense, be unanswerable. Not because of the limits of our technology, but because of the structure of reality itself. The question is, what is on the other side? On the other side of the domain wall Webb's signal implies, beyond the boundary where the inflatant field transitions from our ground state to another, there is a region of space-time. It has existed for as long as our universe has, perhaps longer. It is governed by physical laws close to ours, but not identical. It is expanding in its own way, on its own timeline. And we cannot see it. We cannot send a signal to it. We cannot receive one from it. The boundary is causally opaque. Information cannot cross it in a form that would be interpretable on the other side. That is the silence the signal leaves behind. We've found the wall. We've measured its distance. We've characterized its energy. We've traced its effects on our light, our structure, our sky. We've built the theoretical framework that explains why it's there and what it separates. And at the end of all that work, we stand before a boundary we cannot cross and cannot see through, knowing that something is on the other side and being unable to learn more. This is not a failure of science. It's the discovery of a limit, and limits, in physics, are among the most important discoveries there are. The speed of light is a limit. The Planck scale is a limit. The cosmic horizon, the edge of our observable universe, beyond which the expansion of space makes observation impossible, is a limit. Each of these limits, when discovered, didn't close a door. It opened a new room. The speed of light led to relativity. The Planck scale pointed toward quantum gravity. The cosmic horizon led to inflation. The domain wall, if it's real, is a limit of a new kind. A limit defined not by speed or scale or resolution, but by causal connection. A place where our universe ends and something else begins. Something that shares a mathematical framework with us, that the same equations describe, but that operates separately, evolves separately, and has existed separately since before our star was born. What Webb found in that calibration field is the most profound thing a telescope has ever found. Not an object, not an event, but a boundary. The edge of the only universe we've ever known. And on the other side of that boundary, separated from us by a surface thinner than an atom and more distant than the mind can conceive, the answer rests in a silence that is perfect and permanent. We know the wall is there. There's one aspect of this discovery we've only touched on, and it deserves dwelling on because it touches something deeply human. Cosmology, like all sciences, is a human enterprise. The people who built the standard cosmological model, who spent careers refining lambda CDM, who developed the mathematics of the cosmic microwave background, who built the large-scale structure surveys, the dark energy analyses, the Hubble constant measurements, have invested more than time. They've invested intellectual identity. The framework they built isn't merely a set of equations. It's a worldview, a coherent picture of what the universe is and how it works. When that picture is challenged at its foundations, the response isn't always purely scientific. It's also human. Several of the most prominent advocates for the single universe interpretation of cosmological data have been vocal in their skepticism of the bubble hypothesis. Their objections are scientifically legitimate. The measurement uncertainties are large. The domain wall models have free parameters. The alignment of independent anomalies could be coincidental. These are real concerns that deserve to be taken seriously. The case for the bubble interpretation is suggestive, not conclusive. But some of the resistance has a different character, less about the specific uncertainties and more about prior probability. The argument that a neighboring universe is simply too improbable to be taken seriously, regardless of what the data show, is not a scientific argument. It's an aesthetic one, a preference for a simpler universe, a single universe, a universe whose boundaries are entirely within reach of human investigation. That preference is understandable. It is also, if the data are right, a preference the universe isn't obliged to share. There's a particular poignancy in the position of researchers who have spent decades working within the standard models framework, producing results that are genuinely important and genuinely precise within their domain, only to discover that the domain itself may be smaller than they believed. Their work is not invalidated by the bubble hypothesis. General relativity still holds within our universe. Dark matter still shapes the cosmic web. Acoustic oscillations in the early universe still produce the fluctuation pattern in the cosmic microwave background. All of that remains true and important. What changes is the frame around the picture. The universe those researchers spent their lives describing is still there. It's just not everything. The data don't negotiate. They don't care about careers or paradigms or the elegance of a framework that took a century to build. They don't make exceptions for intellectual investments, however deep or legitimate. They simply are what they are. And what they are regardless of what we'd prefer them to be. In France, the tradition of modern cosmology runs deep. It was a Belgian priest, Georges Lemaitre, trained partly in Paris, who first proposed in 1927 what he called the hypothesis of the primeval atom, the idea that the universe had begun in an extremely dense, hot state and then expanded. That is essentially the Big Bang, before the name was coined. And Lemaitre deduced it from Einstein's equations 2 years before Hubble published his observations of the expansion. The Paris Observatory, founded in 1667, is the oldest continuously operating observatory in the world. It's where Euler measured the speed of light in 1676. It's where generations of French astronomers contributed to building the map of the cosmos that Webb is now redrawing. When we talk about a signal that might rewrite the boundaries of the universe, we're talking about rewriting a map that France helped build for over 3 centuries. And there's an irony in the fact that the telescope that detected this signal sits at the L2 Lagrange point, a concept in celestial mechanics developed by the Franco-Italian mathematician Joseph Louis Lagrange in the 18th century. Lagrange points are positions in space where the gravitational forces of the Sun and Earth balance in such a way that an object can remain there stably. Webb floats at L2, a million miles from Earth, in a position Lagrange calculated 250 years before anyone sent a telescope there. The mathematics of an 18th century man holds in place the instrument that may have just found the edge of reality. That's the kind of continuity that gives you vertigo, the thread connecting an abstract calculation in a Parisian office to a signal from the farthest reaches of the observable universe, crossing centuries the way light crosses space, carrying a message whose meaning changes with every new generation of observers. No one has ever been at the edge of a universe. The concept barely makes sense in classical physics, where space is continuous, infinite, and boundaryless. But in the framework toward which Webb's signal is pushing us, the edge isn't a place in space. It's a transition in the structure of space-time itself. The boundary between 2 bubble universes, the domain wall, is not a wall in the ordinary sense. It's a surface where a field, the inflaton field or its descendants, transitions between 2 stable energy states. On our side, the field has one value. On the other side, it has a different value. At the boundary, the field is in transition, neither fully one nor fully the other. The width of that transition zone depends on the energy difference between the 2 sides. For a low-energy domain wall, the kind Webb's signal implies, the transition zone could be extraordinarily thin. Perhaps as thin as the Planck length, the smallest meaningful scale in physics, roughly 10 to the minus 35 meters. For all practical purposes, the boundary is a surface with no thickness. You cross it in an instant. What the crossing would mean for any physical object, hypothetically, since the boundary is 11 billion light-years away and the concept of traveling to it is not realistic, depends on what exactly changes on the other side. If only the cosmological constant differs, the immediate effects would be subtle. Space would expand at a slightly different rate. The vacuum energy density would have a different value. Over astronomical time, this would compound into dramatic differences in large-scale structure. But in the first moments after crossing, matter and energy would behave recognizably. If more fundamental forces differ, if the electromagnetic constant or the strong nuclear force has a different value on the other side, then atoms themselves would be different. Electrons would orbit at different radii. Chemical bonds would have different strengths. Nuclear reactions would proceed at different rates. Any matter crossing the boundary would find its constituent particles, suddenly governed by the new constants, behaving differently. The crossing itself could trigger a cascade of physical changes at the atomic level, transforming any material that passes through from one set of stable configurations to another. The domain wall isn't simply a physical barrier, it's a causal boundary. Our past light cone, the region of space-time that could have influenced us, doesn't extend through the wall. The neighboring universe has its own past light cone. The two cones don't overlap. Everything that happened on the other side before the bubbles grew close to each other had no causal influence on us, and ours on it. Two universes, adjacent in space, entirely isolated in time. The edge of everything is not empty. It's occupied by the boundary of somewhere else, and somewhere else has been there, just out of reach, for longer than our star has existed. There's something in this idea that resonates with a very old intuition. Blaise Pascal, one of the greatest minds France ever produced, mathematician, physicist, philosopher, wrote in the 17th century, "The eternal silence of these infinite spaces frightens me." Pascal was talking about the void between the stars, the immensity of a cosmos that the telescopes of his age were only beginning to glimpse. But his sentence could have been written for what Webb has just found. Because the silence the signal leaves behind is of a nature even deeper than the one Pascal contemplated. It's not the silence of empty space between stars. It's the silence of a causal boundary. The silence of a wall that information cannot cross, of a universe that is right there on the other side, and that will be forever inaccessible to us. And yet, we found it. With enough precision, enough patience, and a gold-coated mirror floating in the void 1,000,000 miles from Earth, we detected the mark it left on our light. We cannot see through the wall. But we can see the wall. And seeing the wall is knowing that there is something beyond. That may be the most human thing we've ever done. Looking as far as it is physically possible to look, reaching the very limit of what causality permits, and continuing to ask questions about what lies on the other side, even when, especially when, the answer is a silence that is perfect and permanent. The light-carrying Webb's signal traveled for 11 billion years. It left its source before the sun existed, before Earth formed, before life appeared, before any brain evolved to contemplate the origin of everything. It crossed an expanding cosmos, stretching over billions of years, shifting color from visible to infrared, becoming invisible to everything except the most precise instrument humanity has ever built. And somewhere along that journey, it brushed against something. It grazed a boundary. It carried the mark of that contact across the eons, through the expansion, through the darkness, to a gold mirror in the void that had been waiting for it without knowing. The wall is there. The signal is real. And the question of what lies on the other side is the greatest question science has ever asked, not because it's the most complex, but because it's the only one the very structure of reality may forbid us from answering. We know the wall is there. What we may never know is what it guards.